Hey, welcome back everyone. Today we're going to be taking a look at a subject that's very important in Z80 assembly language programming, which is the stack. Now this is a subject I wasn't really sure if I was going to be making a video on, because it's a very common topic that's already been very well covered in other areas, both online and in books, in print and other YouTube videos and so forth. But I thought I would go ahead and create a video on it for my viewers, just for the sake of completeness and just in case people might happen to enjoy the way that I explain things, and just for my viewers who may be beginners who are not familiar with the stack. Although it's a fairly simple concept, there are some parts to it that are quite detailed that we need to be very familiar with so we can use the stack effectively. And so since my videos are aimed at beginners, I just thought it would be important to cover it in today's video for people who might not be familiar with it. So first I'm going to start off by explaining how the stack works by giving kind of a silly example, an analogy that you might find useful in trying to understand how the stack works by comparing it to an example in daily life. Now let's say, for example, you have a barrel by the front door of your house and you come back from doing your grocery shopping and you need to get the keys to unlock your door so you can go into your house, but your hands are full of groceries, right? So let's say that your hands represent registers in the Z80 microprocessor. Let's say your right hand represents the H register and your left hand represents the L register. L for left, so that's easy to remember. So your hands can be thought of as the H and L registers, and together they are the HL register pair, for example. And since each hand is full of groceries, we need to somehow free up our hands in order to grab our keys and unlock our front door. So the way we do that is by putting the groceries into this barrel we have by our front door, because we don't want to put the groceries on the dirty ground, so we have a nice clean barrel there for us to use. And we have a very specific way that we put these groceries into the barrel. And you can think of this barrel as your grocery stack. So first what we do is we unload our H hand, our H register hand, and we put that grocery bag into the barrel. And then we take our L hand, which is our left hand, which represents the L register, and we put that grocery bag into the barrel. So now we have our grocery barrel, or our grocery stack, that has the H grocery bag on the bottom and the L grocery bag on the top. So now our hands are free, we can grab our keys, unlock our door, do whatever we need to do, and then we can grab our groceries back out of the barrel. And we do this in exactly the reverse order by first taking the L grocery bag out of the barrel, because we want our L groceries back in the hand they came out of, and then we grab our H grocery bag out of the barrel, and we have our H grocery bag now back in our right hand. So our H and L hands now contain our H and L grocery bags that were originally in our hands to begin with. And this is how the computer uses the stack. And as we'll see later when we take a look at an example of how we use the stack, it's not always so important that we really know specifically which grocery bag goes in the barrel first and which one comes out first. Although I think it is important for us to be able to know that and understand that in our development journey. So we're going to be taking a look at that in detail a bit later as well. But just so you know, it's not always important that we necessarily know how the computer stores these grocery bags into our grocery barrel. So it's not always particularly important that we know how the computer stores the values in registers, such as the HL register pair, into the stack. So just as our grocery barrel stack is used to temporarily store groceries, the stack in the computer is a location in memory that can be used to temporarily store data, and particularly data that is previously being stored in registers. So if we have data, let's say in the HL register pair, and we want to temporarily store it onto the stack or into the memory location where the stack is assigned, then we've now freed up the HL register pair to be used for other things, and later we can grab the data back from the stack and put it back into the H and L registers. And just as we wouldn't want to leave our groceries in that barrel by the front door very long, we don't want to leave data sitting in the stack forever. We want to just use it as a temporary storage area when we need to temporarily free up some registers. So as I mentioned, it's a very important issue in Z80 assembly language programming, and it's not all that complicated, but there are some pitfalls we need to avoid, and there are some details we need to understand about it. So let's take a look at it right now. Alright, so first what I'd like to do is take a look at a list that I've made of the different topics that I think are important for us to understand about the stack. And before I do that, actually, I want to show you a reference where I learned some information about the stack. And I'm not saying this is the best reference that people should use, and I'm sure it's actually not the best reference. Like I said, there are many different places you can find information about the Z80 Assembly Language Stack on the internet or in books or on YouTube videos. But I was just reading a book that, as you probably know, I love to read old books and new books. I think it's always interesting to find information from any source that I can. And I'm going to share with you a book that I was reading, which is this one here, called 8080/Z80 Assembly Language Techniques for Improved Programming by Alan R. Miller. And this is quite an old book. And as you can see, it also discusses about the 8080 processor as well as the Z80 processor. So it might be kind of confusing for some people who try to read it and they're looking at 8080 instructions that aren't relevant to the Z80 microprocessor. But I think it's kind of cool to look at the information that it describes about the stack. So I'm going to be sharing it with you today. And I've also uploaded a PDF copy of this book to the SpriteWorks Facebook group for my Patreon subscribers. And I'll also put a link to this book in the video description for any of you who might be interested in checking it out yourself. So first of all, let's take a look here at the section that talks about the stack. Alright, so here's a PDF of the book, and I'll just go to the table of contents here and look for the section that talks about the stack, which is actually right here, Chapter 3, the stack. So let's go take a look at Chapter 3. And remember how I mentioned that the stack is a location in computer memory where we can temporarily store data that is contained in registers. Well, if we take a look here, it shows how that data is actually stored in those memory locations. It's stored using what's called a last in, first out method, which is shown right here. It says the last in, first out LIFO buffer. That's what LIFO stands for, last in, first out. And here's how it works. So you can see when the data goes in, it goes to the back here, and then all the new data gets pushed in front of it. And so the last piece of data that gets pushed onto the stack is the first piece of data that gets pulled out of the stack. So I'll just go back to my list of details that we want to cover about the stack today, which is right here. So the Z80 Assembly Stack, there are some details that I think are important for us to know about it. And first is the reference book that I just shared with you. And if you're interested in taking a look at that book, then to follow the link in the video description. But I'm sure there are many other better references you can use if you like, if you're not particularly interested in learning information from very old books. But I think it's kind of interesting to look at. And so that's the reference that I'm going to look at today. And the next point here is the description. So I kind of briefly introduced you to how the stack works in my analogy using the grocery bags. And then we just followed up a bit on that description by taking a look at the last in, first out operation of the stack. But now let's take a look at exactly how we use the memory locations as a stack. So the next point on my list here talks about the stack pointer. And the stack pointer is a pointer that tells us where the stack is in memory. So now I want to take a look at this specifically by opening up the ZX Spin assembler or the ZX Spin development environment. And if you're not familiar with ZX Spin and you want to follow along with me, you can go ahead and take a look at the video where I explained how to install it and how to use it. So let's take a look at that now. Alright, so here I have the ZX Spin assembler, well actually the integrated development environment showing on my screen, which has the assembler over here and the emulator over here, and back here we have a window which is the debugger, and we'll get to these items in a moment. But the first thing I want to show you is how we can actually examine the stack in the computer memory. And the next topic I want to talk about is something called the stack pointer, which is a pointer that tells us where the stack is currently being indicated in the computer memory. So if we go over here to the disassembler or the debugger, we can take a look at this section here. You can see here there's a section called registers, which is selected right now. And over here there's an SP register, which stands for stack pointer. And the stack pointer is a register that contains a value, which is a memory address, which contains the location of the last item that was placed onto the stack. So the next thing we want to do is take a look at how we actually place items onto the stack. So let's go back to my list here, and we can see that my next point here says that it grows downwards. So what does that mean? Well, the area in memory that contains the stack or is assigned as the stack, it gets filled up with data, obviously, as we push values onto the stack, which we'll be looking at in a moment. But obviously, once we store values or store data into memory that's assigned as the stack, it needs to change the value of the stack pointer so the computer knows where to put the next piece of data. And the way it does that is it grows downwards in memory. And what that means is the stack pointer starts at a certain memory address. Let's say, for example, the memory address that we want to use for the stack is location 9000 in memory, 9000 hexadecimal. And then every time we save data onto the stack or into the memory locations assigned as the stack pointer would count downwards from that memory location. So normally when we think about storing data in memory, we think about storing the first piece of data at a memory address, and then the next piece of data would be in the next memory address higher, and then the following pieces of data would keep counting up in memory. But the stack works differently. The stack counts downwards. So as we add new data to the stack or into memory, which is assigned as the stack, the memory addresses actually count downwards. So for this reason, we normally want to assign the stack a location in memory that is near the top of the memory because it's going to be counting downwards. And we'll take a look at that in a moment as well. But before we do, there's one more point here I want to cover, which is point number 4 here, which says the operation of it, and it says 2 bytes. So what that means is when we store data into the stack, we store data 2 bytes at a time. And just as we used the analogy with the grocery bags in our hands, we had 2 hands representing 2 registers, the H register and the L register in our example. Of course, they can be any registers, they don't have to be the H and L registers. But in that example, we had groceries in both of our hands, and we unloaded both of those grocery bags and freed up both of our hands. And that's exactly how the stack operation works as well. We store 2 bytes at a time, so both the H and the L register, for example, would be saved to the stack as 2 bytes, one for the H register and one for the L register. So now that we've been introduced to these 3 different points here, the stack pointer, which keeps track of the last piece of data that was pushed onto the stack, the fact that the stack grows downwards in memory, so it starts at a higher memory address and it counts down as we add new data to the stack, and then finally this point where the operation of it is that it stores 2 bytes at a time. So just keep those 3 points in mind, and now we're going to take a look at specifically how the stack works. And let's take a look at this section here that's called storing data onto the stack. And here, like I mentioned before, this book talks about both the 8080 and the Z80 microprocessor. So here you can see there's notes about the Z80 microprocessor and the 8080 microprocessor. So if you do happen to read this book, you can just probably ignore any 8080 references that it makes and just focus on the Z80 parts. But let's go down and take a look at how we would store information or data onto the stack. And this book contains a really cool diagram here, which you can see is really old school using these ASCII characters. I think it looks kind of neat, and it explains exactly how the stack operation works. So first let's take a look right here where it says Z80 and it says push HL. So this is an example that I explained earlier using the grocery bags where we want to save those grocery bags into our grocery stack. Well, here we want to save the information in the HL register pair onto the stack. And we do that using this push instruction. We push the information that's currently in the HL register pair onto the stack. And what that means is it copies the information from the HL register pair to the memory locations that are assigned as the stack. And one thing to keep in mind as we're discussing how this data gets transferred back and forth between registers and memory locations that are in the stack, we need to remember that these operations actually copy the data. They're not actually moving the data from one location to the other, but they're actually copying the data from one location to the other. Now let's see exactly how that works. So this push HL instruction here operates like this. So if we take a look at this diagram here, we're going to just read through the instructions of how this book describes how the stack works. So remember I talked about the stack pointer. So the stack pointer is a register that contains a memory address where the last piece of data was pushed onto the stack. So in this example here, if we take a look at this diagram, If you take a look at this section over here on the left, it shows the stack pointer is pointing to this top section here, which is a memory location that corresponds to, in this example, address 4000 hexadecimal. So on the left here, this is before we do any pushing, and the stack pointer is pointing to memory location 4000, and there's nothing contained in any of these memory addresses. So the top memory address here is location 4000, and then the one beneath it, because remember the stack grows downwards as we add information or data to it. So the memory location below that would be 3FFF right here, and then the memory location before that right here would be 3FFE. So you can see in this example, our stack is assigned starting at memory location 4000 hexadecimal, and we'll see in a moment how we can manipulate that manually. So in this example, our stack pointer is pointing to memory address 4000, and nothing is contained in the stack at all. So now let's take a look at exactly what happens when we store information onto the stack using this push instruction right here, push HL. So in this example, we're going to push the information or store the information that's currently in the HL register pair onto the stack. So let's see how that happens. So let's take a look at the text right here. It says the stack pointer is decremented, then the H register, the high half, we know that the H register is the high register in the HL register pair. So it says the stack pointer is decremented, then the H register, the high half, is copied to the stack. And let's take a look at that in the diagram right here. So here we just explained that the stack pointer starts off by pointing at memory address 4000, and then the text here says the stack pointer is decremented. So in the second part of the picture here, this is when we execute the push HL instruction. And in the computer, the push HL instruction actually happens in 2 steps. Just as when we were loading our groceries into the barrel, we did that in 2 steps. We unloaded our right hand, which is the H register hand, and then we unloaded our left hand, which is the L register hand. Well, the computer does exactly the same thing. First, it's going to take the groceries out of our right hand, which is the H register, and put that onto the stack. So that's what it's doing right here. You can see in the center part of this picture, first it's decrementing the stack pointer. So now the stack pointer has been decremented from address 4000 down to address 3FFF, and then it stores the information from the H register into that memory location, which you can see right here. The HL register pair is here. This is the H register, which has this high word written inside of it, and then the L register is here, labeled as low. So the data from the H register gets copied into this memory location 3FFF, and that's the first part of the push operation that the computer executes internally. And then what it does next is it needs to store, obviously, the information from the other register, which is the L register. And if we take a look at the text again, up here it says the stack pointer is decremented a second time, and the L register, the low half, is copied to the stack, which is shown right here. In the third part of this diagram here, you can see the stack pointer has now been decremented down to this bottom memory location, which is labeled in this case 3FFE, so it's been decremented by 1, and then the data in the L register, which is the low register, gets copied into that memory location right here. So you can see how this push HL operation works. Is first the stack pointer gets decremented once, and the contents of the H register get saved into that memory location, and then the stack pointer gets decremented a second time, and the contents of the L register get saved into that memory location. So after that push HL instruction has been completed, this is what the computer looks like. The stack pointer is now pointing at this address 3FFE because it started at address 4000 and it was decremented twice in this process. And now the stack looks like this. Address 4000 contains just whatever data was there before, because we didn't do anything with the data at that address. But then these two addresses below it, 3FFF and 3FFE, contain the data from the H register and the L register respectively. Alright, so that should be pretty simple to understand, I think. It's not a very difficult concept we're looking at. We're basically just storing data into memory locations, and we can see now how the stack pointer gets decremented twice as we push 2 bytes onto the stack, because we always push 2 bytes at a time onto the stack. And in this example, we push the data from the HL register pair onto the stack, and obviously that's 2 bytes because the H register is 1 byte and the L register is another byte. And now let's take a look at how we retrieve information from the stack. So we're going to take the data that we previously pushed onto the stack, and we're going to pop it off of the stack and we do that appropriately enough using the pop instruction. And let's take a look at how that works. But before we actually take a look at the details of how that works, let's take a guess at how that should work based on the information we just learned about how the push instruction works. So the pop instruction works precisely in reverse of the push instruction. So now instead of copying information from a register pair and putting it onto the stack, we want to copy information from the stack to a register pair. And one thing to keep in mind here is that we don't necessarily need to pop the information or retrieve the information back into the same register pair that it came from, which is in this case the HL register pair. We could retrieve the information or retrieve the data and put it into a different register pair if we wanted to. We could put it into the BC register pair or the DE register pair, or we could, if we want to, put it back into the same register pair it came from, which is the HL register pair. So let's see if we can figure out how the pop instruction would work to allow us to retrieve data from the stack and put it back into the HL register pair in this case. So all we're going to do is simply reverse the process, and the last operation that took place was the data from the L register was stored onto the stack. So to reverse that, we just take the data from the stack and put that back into the L register, and then we increment the stack pointer instead of decrementing it. So we go over to the left here, and now the stack pointer gets incremented up to the next memory location, which in this case is 3FFF, and that's the location where we stored the data from the H register. So now we have to extract that data and put it back into the H register, which would be the reverse of this second step here. We're going to take this high data byte and put it back into the H register. And then finally we do the reverse of step 1 here, where we're going to be incrementing the stack pointer a second time back up to the top level here, which would bring it back to location 4000 hexadecimal, where it all began. Now let's take a look at the written description and another diagram showing exactly how that works, which is right here below it. It shows you right here. The pop instruction reverses the push process. And if we take a look at this paragraph, it actually shows an example where we're going to be retrieving the information and putting it into a different register pair. In this example, it says, for example, a pop DE command copies 16 bits, which is 2 bytes, from the stack into the DE register. So in this case, in this example, the book is taking the information from the HL register pair, pushing it onto the stack, but then it's going to pop that information, those 2 bytes of data, into the DE register pair instead of the HL register pair, which is perfectly fine. That's perfectly legal. You can do that. And let's just read the description of how the book says this happens. It says, because the stack operates in an LIFO manner, which is last in, first out, the most recently added byte is removed first, which we just took a look at. And it says this is placed into the register E. Since E represents the low byte in the DE register pair, it's going to extract information from the stack and put it into the low byte, which is E, first. And then it says the stack pointer is automatically incremented, and the next byte is transferred from memory to the D register, which is the high half of the DE register pair. And then finally it says the stack pointer is then incremented a second time. Figure 3.4 demonstrates this operation. So let's take a look at this figure right now, which is right here. And this might look confusing with the arrows and the lines and everything, but it's really not. So let's just go through it, and we'll see this is how we start off. After our initial push operation, the stack pointer is now pointing to this bottom memory location here, which is 3FFE, and that's where the data from the original L register was stored, which is the low register, and we want to extract that into the DE register pair now. And this is how the computer does it. So when we want to extract the data or pop the data off of the stack, all we need to do is execute this pop DE instruction right here. We don't need to concern ourselves with which piece of data is going into which register, the D register or the E register and the H register and the L register. The computer handles that all automatically for us, but we should understand exactly what the computer is doing. So if we take a look at our diagram here, it shows the stack pointer starts off at the bottom location, which contains the low register data, and it moves it into the low register right here, which in this case is the E register. So then in the second part of this operation, we can see the stack pointer here has been incremented up one level up to memory address 3FFF, and then this arrow here shows that the high data is retrieved from the stack and put into the D register, which is the high register of the DE register pair. And then finally, the third part of this operation increments the stack pointer a third time and moves it back up to this initial starting address, which in this case was 4000 hexadecimal. And now let's take a look at the last sentence of this paragraph, because it contains some important information. And it says, notice that the data originally pushed onto the stack is still present, which you can see right here. In this last picture here, it shows that the stack pointer is now pointing to the original top address, which is 4000 hexadecimal in this case. But you can see that these two lower addresses, 3FFF and 3FFE, still contain the data that was originally in the high byte and the low byte. So obviously these high and low words actually represent data or a single byte value. So this memory location 3FFF would contain a numeric value between 0 and 255 decimal, as would this one here, which contains the low byte. 3FFE address would contain a byte of data which would range between 0 and 255 decimal, or 00FF hexadecimal. And that's essentially how the stack works. We have a stack pointer which starts off pointing at the location where the last piece of data was pushed onto the stack, and then data gets saved onto the stack with a push operation and pulled off of the stack with a pop operation. Now let's go back to our ZX Spin development environment and take a look at how this actually works in real life. And if you want, you can follow along with me and I'll show you exactly how we do that. Alright, so here we are in our ZX Spin development environment. And you can see I have the emulator over here on the left and I have the assembler over here on the right. We're not going to be actually using the emulator part of this environment today, but I also have the debugger window here open behind it, which we will be using. So let's first of all just take a look at my assembly language program and see what I've got going on here. And here it is right here. So the top line of our program right here is an org instruction, which we all know how that works. It tells the assembler where to store our data in memory after it gets assembled. And then the first line of our program is a load instruction, and it's going to load a value of 9000 hexadecimal into the HL register pair. And our comment here says value to load into SP. So SP is the stack pointer register, and I want to manually load a value into the stack pointer because we can actually manually manipulate the stack pointer and have it point wherever we want in RAM memory. So we can actually move the stack around in memory if we want to, and all we need to do in order to do that is load a value into the stack pointer register, and then the computer will look at that location in memory for the stack. So this is what I'm going to be doing in this program. In this case, I'm taking the value of 9000 hexadecimal and I'm loading it into the HL register pair. And the reason I'm doing that is because in this next line here, I'm going to be copying that value into the stack pointer register, which it says here in my note, load stack pointer. And we'll take a look at this program in detail in the disassembler or in the debugger, so we'll see exactly how this works. But let's just go through it quickly so we know what we're going to be looking at in a moment. So the next line of my program here says load HL ABCD hexadecimal. So this is going to again use the HL register pair, and it's just going to load a random value into it. In this case, a value of hexadecimal ABCD, which is a valid hexadecimal value. And in this case, the AB part of this value is going to be loaded into the H register, and the CD part of this value is going to be loaded into the L register, just because that's how the load instruction works with a 16-bit register pair. And my note here says value to push. So now I'm putting a value into the HL register pair in order to prepare to push it onto the stack, which I do in the next line right here, push HL. So this line, you can tell by the note, says push to stack. So now we're going to be pushing the values in the HL register pair onto the stack. And then in our next line here, we have a call instruction, which calls a subroutine that I've labeled sub1, which is right down here, which we'll take a look at in a moment. So this line is going to call a subroutine at this sub1 label. And that's why my note here says call sample subroutine. This is just a sample subroutine. It doesn't do anything useful. It's just to use in this example. So it's not actually doing anything that we need it to do other than calling a subroutine. And then the next line of the program here says XOR A. Again, this is just a dummy piece of code that I'm not using it to do anything useful. As you'll see in a moment, I'm just using this so that we have some instruction that we can see where our program is operating in memory and where the data is in our program. Now finally, we'll just take a look at my subroutine here, which is a sample subroutine labeled sub1. And the first line of this subroutine, again, is another dummy instruction. It's a dummy code, which just gives us a reference we can use when we're examining this program so we can see where we're at. So we don't actually need this ORA instruction to do anything useful for us. It's just a dummy instruction. And then finally, we have our last return instruction here, which says return from sub1. So this return instruction is going to return control of the program back to the main program loop, which called it up here. And so this is kind of a pop quiz if you can spot any problems with this program the way it's currently written. And I'm sure the more experienced of you will be able to spot it right away, is that it's missing a main return instruction for this main program loop up here. So we have one return instruction here, which is going to return control of the computer back to the part of the program which called this subroutine. But then this main part of the program up here, which is our main program loop, also needs its own return instruction. So let's enter that right now. Return. And this instruction will return control of the computer back to the basic program which called this machine code program to begin with. So I'll just make a note here, return to basic. Just like that. And now let's take a look at our debugger and see what this program actually does. Alright, so here's our debugger right here. And let's see how this program works. So you can see our org instruction here tells the program to be loaded in memory location 8000 hexadecimal. And in this debugger, if you go to the view menu option up here, you can see I have this hex numbers option selected. So my numbers are being shown in hexadecimal. And let's go take a look at address 8000 hexadecimal. And I'll just type that in here, $8000, enter. So there we are. We're now taking a look at location 8000 in memory, which currently contains zeros because I haven't assembled this program yet. So let me go ahead and assemble it. And let's go back to our list of items we wanted to cover in this video. So let's go back here and take a look at the stack pointer. So over here you can see in our registers list, here is our stack pointer register right here called SP. And you can see it currently contains a value FF48 in hexadecimal. And you can see the first two lines of our program are going to change that stack pointer value. But first we need to load this 9000 value into the HL register pair. So let's just step through our program and go ahead and do that. And you can see here our HL register pair currently contains 10A8. So let's go and step through this program instruction and we should see that change to 9000. So let's go ahead and do that now. But first we need to change our program counter to 8000 hexadecimal because that's where our program actually begins. So here our program counter needs to change to 8000 hexadecimal. So I'm just going to change it manually by entering 8000, just like that. So now if I press this step button, it will execute the instruction at location 8000, which is load HL 9000 hexadecimal. So let's go ahead and do that right now. And there we go. So we've executed this load HL 9000 hexadecimal instruction. And now our HL register pair here contains a value of 9000. And let's see what our next instruction does. Our next instruction is going to take the HL register pair contents, which is 9000 hexadecimal, and load it into the stack pointer. So let's take a look at our stack, which if you take a look over here, there's a tab labeled stack, and I'm just going to click on that. And now we can see that this is our stack. And on our registers tab here, our stack pointer has a value of FF48, which is just a random value for now. So let's take a look at our stack window. And you can see here's that value, FF48. And you can see it's colored dark. So that means it is the current value of the stack pointer, which is FF48. And it contains a piece of data, which in this case is 15FE. And just to let you know, this debugger displays the contents of the stack memory addresses as 2-byte values. So it doesn't separate the different bytes into the individual high and low bytes. It just shows us one memory address, which is the value of the stack pointer, and it shows us the combined 16-bit value that's stored at that address, which would actually be that address and the next address. So it would be, in this case, FF48 and FF49. So let's just go back to our program and continue taking a look at what our program instructions are going to do, which in this case, it says load SP, which is the stack pointer, with the value that's in HL, which we know is 9000 because we just loaded it in the previous step. Right here you can see HL contains 9000. So let's go ahead and execute that. And there we go. I've executed this instruction here, load SPHL, and what that did was take the value that's in HL, which is 9000 hexadecimal, and load it into the SP register, which is the stack pointer, which we can see right here. The stack pointer now contains a value of 9000. So this is how we can manually manipulate the stack pointer to have it point to any location in memory that we want. So what does that mean? Well, that means the next time we use a push instruction, it's going to decrement this stack pointer and load 2 bytes into memory. So now if I take a look at this value, 9000 in our stack, which is right here, you can see the value 9000 is darkened, which means it's the current active stack pointer value. And just take note that this stack is shown kind of upside down. It has the higher memory addresses at the bottom and the lower memory addresses at the top. So as we add data to the stack, it's actually going to grow upwards on my screen, but actually downwards in memory. So now we've manually changed the stack pointer to point at location 9000 hexadecimal in memory, which means that's the location where the computer thinks is the last byte of data that was pushed onto the stack. But obviously we haven't pushed any data onto the stack yet, so we're going to be doing that in a moment. Now our next line of code here says load HL with ABCD hexadecimal. And we'll go back to our register window, and our HL register pair is right here, which currently contains a value of 9000. So if we execute this instruction now, you can see our HL register pair now contains a value of ABCD. So what are we going to do next? Well, the next thing we want to do is right here, we're going to push the HL register pair onto the stack. And you can see our HL register pair contains ABCD. So now if we take a look at our stack pointer is right here, 9000. And so what it's going to do, as we just took a look at, is it's going to decrement the stack pointer twice. And while it's doing that, it's also going to push the value from the HL register pair onto the stack. So when we execute this instruction, we would expect that the value that's currently in HL, which is ABCD, should get pushed onto the stack right here. So let's go ahead and do that now. And there we go. Now the stack contains a value ABCD, and the stack pointer is pointing at 8FFE, which is 2 addresses below what it previously was, which is 9000, because it gets decremented twice during the push process. And now 8FFE is the current value of the stack pointer, which indicates the memory address of the last piece of data that was pushed onto the stack. And so the next line of our program here is a call instruction. It's going to call our subroutine, which over here in our program is called sub1, which is down here, sub1, which we can see in our debugger is at address 800D hexadecimal, which is right down here, 800D right here. So this is where our subroutine is located in memory. And here it shows it contains an instruction OR A, which is correct if we look at our program over here. OR A is the instruction in our subroutine, and that's followed by a return instruction. But now let's go back to this instruction that we're about to execute, which is a call instruction. And before we execute that instruction, let's go back to our list of details for this video, which is right here. We've taken a look at the stack pointer. We've taken a look at the fact that the stack grows downwards as we add data to it. And we now know that the operation of the stack operates in 2 bytes at a time. It saves both the high byte and the low byte in memory with one operation, the push operation. And now the next point here is called calls. So why are we interested in the call instruction as part of our video on the stack? Well, the reason we're interested in the call instruction is because the call instruction actually manipulates the stack. So let's go back to our debugger here, and let's see how the call instruction actually manipulates the stack. Well, before we execute this instruction, let me explain to you how it works. So the call instruction is going to call a subroutine, which means it's going to transfer execution of the computer over to another location in memory where our subroutine is located. But obviously that subroutine is going to end at some point, and there's going to be a return instruction to return control of the computer back to the original part of the program that called it, which you can see right here is our return instruction. It says return from sub1. And where is that return instruction going to return control of the computer to? Well, since this subroutine was called right here, it says call sub1. After that subroutine finishes executing, return of the computer should come back to this line here, which is our XOR A instruction. But how does the computer know where to continue execution of the program from? Well, the way it does that is it takes the value that's in the program counter and it stores that information somewhere. And where does it store it? Well, it pushes it onto the stack. So you can see the call instruction manipulates the stack by pushing the value of the program counter onto it, so that when the subroutine returns control back to the program that called it, the program will then retrieve that program counter from the stack and continue executing the program from where it left off. So let's continue with our program and see exactly how that works. So here we have a call instruction, and we would expect this call instruction to push the program counter onto the stack. So if we take a look at our registers again, we can see our program counter contains a value of 8008. But now when this call instruction pushes the contents of the program counter onto the stack, we have to remember that it's not storing the current contents of the program counter, but rather it's going to store the contents that need to go into the program counter so the computer knows where to continue executing the program after it returns from the subroutine. So right here at address 8008, that's the current content of our program counter here. And this instruction is going to call our subroutine, but then once the subroutine returns, where is the program going to continue executing from then? It's going to go down to this instruction here, which is at address 800B. So since this is where the program needs to continue execution after returning from the subroutine, this is the address that's going to get pushed onto the stack. So let's watch that happen. So here our call instruction is ready to be executed. So let's step through that instruction and we'll watch what happens with the stack. And let's take a look at our stack here so we can see the data that gets pushed onto it. And now let's execute this call instruction, and we would expect this address here, 800B, to get pushed onto the stack. So let's go ahead and check it out. And there you go. You can see that our call instruction pushed this value 800B onto the stack because that is the address of the next instruction that needs to be executed after control of the computer returns from the subroutine we just called. So now here we are in our subroutine, which has an OR A instruction, which we're not interested in. It's just a dummy instruction. You can see here's our subroutine here that has an OR A instruction. So here we are over here, ready to execute our OR A instruction. So let's just step through that. And now that's completed, and we're at our return instruction right here. So once we execute this return instruction, what's going to happen? Well, control of the computer is going to return back to the program that called this subroutine, which was back up here. It was called here, so the program is going to continue execution at the following instruction, which is down here at this line at address 800B, which has conveniently been pushed onto the stack right here. So what's going to happen when we execute this return instruction is the computer is going to pop this address 800B off of the stack, and it's going to put it into the program counter here so that it knows where to continue execution of the program. So let's go ahead and watch that happen. So let's go back to my stack window here, and you can see 800B is currently dark, which means it's active. That's the last piece of data that was pushed onto the stack. So let's go ahead and step through our program and execute this return instruction right now. And now you can see this memory address here is no longer dark. It's light gray, which means this is no longer valid data on the stack as far as the computer is concerned, because it's popped it off of the stack. And where did it put it? Well, as we just mentioned, this 800B address should now be in the program counter, which it is. 800B is right here in the program counter, because it needs it to be there in order for the computer to know where to continue execution of the program. So now our program is back here at address 800B, back in the main program loop up here, and it's ready to execute the next instruction, which is right down here, XOR A, which again is a dummy instruction that we don't care about. It's just to let us see where we're at in our program. But the important thing for us to understand from this is that a call instruction manipulates the stack by pushing an address onto it, which is the address that needs to go into the program counter once execution of the program returns back from the subroutine. So what I'm going to do is modify this program now. Instead of an OR A dummy instruction, what if we do a pop instruction here? So I'll say pop BC, just like that. So what will this do now? So if we take a look at our program, up here, we're pushing the value that's in HL to the stack, and then we're immediately calling a subroutine, sub1, and all this subroutine does is pop a value off of the stack and put it into the BC register pair. And this is one of the things that we need to be familiar with in regards to the stack, because many problems can be introduced in a Z80 assembly language program by mishandling the stack. So we need to be very careful how we use the stack. and this is probably one of the main things we need to look out for. So upon initial examination of this program, someone might expect that since we're pushing the HL value onto the stack up here, and then we're immediately calling a subroutine, which pops a value off of the stack and puts it into the BC register pair, we might expect the value that was in HL to end up in the BC register pair, because we push it onto the stack here, then we call a subroutine, and the subroutine pops that value off of the stack and puts it into the BC register pair. Now you should probably understand where the problem is with this program and why we have to be careful how we use the stack. But just so it's perfectly clear, let's go ahead and assemble this program, and we'll take a look at it in operation. So we'll go back to memory address 8000. I'll change the program counter to 8000, and we'll take a look at the stack. So the first thing we're going to do again is load the value 9000 into HL. So let's go ahead and do that. And now you can see HL contains 9000 hexadecimal. So our next line here is going to load that value 9000 into the stack pointer. So let's go ahead and do that. And there we go. Our stack pointer now contains a value of 9000. So our stack should be pointing at the address 9000. Let's take a look at it right here. And there it is. 9000 is currently dark. It's the last dark value on our stack. It's the lowest memory address, which is shown darkly on this particular window. So we know that this is where our stack pointer is currently pointing, which we can confirm just by looking here at the stack pointer on our list. And now let's go ahead with our next instruction, which loads the HL register pair with a value of ABCD. HL contains a value of 9000. So let's execute this instruction right now. And there, our HL register pair now contains a value of ABCD. Now we're going to push this value onto the stack right now. So we'll go ahead and do that. And first let's change our window here to the stack, and we'll watch it happen right now. There we go. Our ABCD is now showing here as dark, which means it's currently active on the stack. And now we're ready to call our subroutine. So let's see what happens on the stack when we call our subroutine. So I'll step through this instruction, and there I've just called the subroutine right here, and now you can see ABCD is no longer the last value on our stack, because of course, as we just saw, the program is going to push a value onto the stack, which represents the address where it continues execution once the program returns from the subroutine, which is this address right here, 800B. So if we try to pop a value off of the stack in our subroutine, which we are trying to do right here, you can see our next instruction with this green arrow. That's our next instruction going to be executed. It's a pop instruction, and it's going to pop a value off of the stack and put it into the BC register pair. So we might have expected the HL value, which is ABCD right here, to be popped into BC if we didn't understand how the computer manipulates the stack when we use a call instruction. So if we execute this instruction now, pop BC, and we'll go ahead and do that. There you can see our 800B address is now gray, which means it's no longer valid on the stack. But remember, this is the address that the computer needs to know about in order to be able to continue executing the program once it returns back from the subroutine. And this ABC value that we might have expected to be popped into the BC register pair is not in the register pair because it's still on the stack. And we can verify that by taking a look at our registers here. You can see our BC register pair, which is right here, contains this value 800B, which is the address that the computer needs to continue its operation once it returns from the subroutine. So you can see what kind of effect this is going to have on your program execution if you're not aware of this particular detail. And now in this instruction, return, our program is supposed to return back up here to the next line after we called it up here in our main program loop. It should return back down here to this XOR A instruction, which if we take a look in our program, is right here at address 800B. But now since we misused the stack by popping that value into the BC register pair here, the computer can no longer pop that address and put it into the program counter. So if we go ahead and execute this return instruction now, what is going to happen? Well, the computer is still going to pop some value off of the stack and put that into the program counter because that's the only mechanism it has to continue execution of the program after it returns from a subroutine. But now if we take a look at our stack, the value that it's going to be popping is this ABCD value, which was previously in the HL register pair. So let's go ahead and execute this return instruction right here. There you go. So now this ABCD value you can see is gray. It's been popped off of the stack. And where did it go? Well, it went right here into the program counter, ABCD. So this is something we need to be aware of when we push a value onto the stack. We have to make sure that we pop it off of the stack in the proper order, in the proper location, in the proper module, in the proper subroutine, in the proper part of the program. Otherwise, we can introduce these types of problems. So now if we take a look at our program counter having this value ABCD, look where our green arrow is now. Right here, it's a memory address ABCD. So now instead of the computer returning control of the program back to where it should be, which is this XOR A instruction, it's now at this address ABCD, which is going to obviously crash our program, and that's not what we want to have happen. So how could we avoid this situation? Well, there are two main ways to avoid it that I'm aware of. One way is to do some manipulation of the program counter within our subroutine, which is possible. We can do that. If we wanted to, we could increment and decrement the stack pointer as necessary to make it point to whatever data that we need it to point to when we're doing these manipulations in our subroutines. And if we're very aware of what our subroutine is doing and what data is stored in the stack while the subroutine is running, we can, if we want to, manually manipulate the program counter to make sure that it points at that return address that we need it to point to when we return from our subroutine. But I think an easier way to do this would just be to avoid having to manipulate the program counter altogether, which in this case would be very easy. Instead of having our subroutine put a value into the BC register pair, we could just put that value into the BC register pair before calling the subroutine. Right? Instead of putting this ABCD value into the HL register pair, for example, I could have put it into the BC register pair to begin with, or maybe I could put it in the HL register pair initially and then put it into the BC register pair before calling the subroutine. But the point I'm trying to make is that I think, at least in my programming journey, when I'm making Z80 assembly language programs, I'm going to try to just eliminate having to manually manipulate the program counter whenever possible, in order to avoid this potential type of problem. And let's go back to our list one last time here. And you can see we've covered how call instructions work and what effect they have on the stack. And the last detail we need to look at is push and pop usage to preserve stack integrity. So that's what I just mentioned about, is how I'm going to try to avoid any manual manipulation of the stack pointer whenever possible. And hopefully that should help prevent some bugs in my Z80 assembly language programs. Alright, so there we have an introduction to how the stack works in our Z80 assembly language programs. And it's not an extremely detailed, in-depth look at the stack, although it took me a long time to explain, as it always does, because I like to target these videos to absolute beginners, for people who might not be familiar with these concepts. But this gives us an introduction to, I think, some of at least the most important points that we need to consider when using the stack. So, as always, thanks for watching. I hope you're doing well on your programming journey and your game development journey, and we're going to keep moving along, and we'll see you in the next video.